In this video, we will discuss one-way ANOVA. The analysis of variance, or ANOVA methods we use in this class require the F distribution. There is a different F distribution for each different pair of degrees of freedom for numerator and denominator. First, the F distribution is not symmetric, it is skewed right. Second, values of the F distribution cannot be negative. And third, the exact shape of the F distribution depends on the two different degrees of freedom. One-way analysis of variance is a method of testing the equality of three or more population means by analyzing sample variances. One-way analysis of variance is used with data categorized with one factor or treatment. So there is one characteristic used to separate the sample data into the different categories. The term treatment is used because early applications of analysis of variance involved agricultural experiments in which different plots of farmland were treated with different fertilizers, seed types, insecticides, and so on. Table 12.1 on page 567 uses the one treatment or factor of blood lead level. That factor has three different categories: low, medium, and high blood lead levels. Requirements of analysis of variance. The populations have distributions that are approximately normal. This is a loose requirement because the method works well unless a population has a distribution that is very far from normal. There are other tests for populations that are very far from normal, but we won't discuss those in this class. The populations have the same variance, sigma squared, or standard deviation sigma. This is a loose requirement because the method works well unless the population variances differ by large amounts. It has been shown that the largest variance can be up to 9 times the smallest variance, and the results of ANOVA will continue to be essentially reliable. Third, the samples are simple random samples of quantitative data. Fourth, the samples are independent of each other. They are not matched or paired in any way. And fifth, the different samples are from populations that are categorized in only one way. Procedure for testing H0 equals, H0 is M1, mu1 equals mu2 equals mu3 equals a bunch of other stuff equals mu k. First, use technology to obtain results that include the test statistic and p-value. Second, identify the p-value from the display. The ANOVA test is right-tailed because only large values of the test statistic cause us to reject equality of the population means. Third, form a conclusion based on these criteria that use the significance level alpha. If the p-value is less than or equal to alpha, reject the null hypothesis of equal means and conclude that at least one of the population means is different from the others. If the p-value is greater than alpha, fail to reject the null hypothesis of equal means. As always, I strongly recommend that you find technology that works for you and learn how to use it. There are myriad resources online for learning how to use calculators and statistics software. Because the calculations for one-way analysis of variance are messy, we recommend using technology with this study strategy. First, understand that a small p-value, such as 0.05 or less, leads to rejection of the null hypothesis of equal means. If the p is low, the null must go. With a large p-value greater than 0.05, fail to reject the null hypothesis of equal means. Second, develop an understanding of the underlying rationale by studying the examples we will discuss in these slides, which are, of course, also in the textbook. Use the performance IQ scores in table 12.1 and a significance level of alpha equals 0.05 to test the claim that the three samples come from populations with means that are all equal. Requirement check. Based on the three samples listed in table 12.1, the three populations appear to have distributions that are approximately normal, as indicated by normal quantile plots. The three samples have standard deviations that are not dramatically different, so the three population variances appear to be about the same. On the basis of the study design, we can treat the samples as simple random samples. The samples are independent of each other. The performance IQ scores are not matched in any way. The three samples are from populations categorized according to the single factor of lead level. The requirements are satisfied. The null hypothesis and the alternative hypothesis are as follows. H naught is mu1 equals mu2 equals mu3. H1 is at least one of the means is different from the others. The significance level is alpha equals 0.05. Step 1, use technology to obtain ANOVA results. Here are 7 different displays on, there are 7 different displays on pages 570 and 571 of the textbook. Here is the stat disk display, for example. In addition, step 2, in addition to the test statistic of F equals 4.0711, the displays all show that the p-value is 0.020 when rounded. Step 3, because the p-value of 0.020 is less than the significance level of alpha equals 0.05, we reject the null hypothesis of equal means. There is significant evidence to warrant rejection of the claim that the 3 samples come from populations with means that are all equal. Using the sample of measurements listed in table 12.1, we conclude that those values come from populations having means that are not all the same. On the basis of this ANOVA test, we cannot conclude that any particular mean is different from the others, but we can informally note that the sample mean for the low blood lead group is higher than the means for the medium and high blood lead groups. It appears that greater blood lead levels are associated with lower performance IQ scores. Caution: when we conclude that there is sufficient evidence to reject the claim of equal population means, we cannot conclude from ANOVA that any particular mean is different from the others. There are several other methods that can be used to identify the specific means that are different, and some are discussed later in the section. Larger values of the test statistic result in smaller p-values, so the ANOVA test is right-tailed. The figure below shows the relationship between the F-test statistic and the p-value. Assuming that the populations have the same variance sigma squared as required for the test, the F-test statistic is the ratio of these 2 estimates of sigma squared, variation between samples and variation within samples. F equals the variation between samples divided by the variance within samples. The numerator of the F-test statistic measures variation between sample means. The estimate of variance in the denominator depends only on the sample variances and is not affected by the differences among the sample means. Consequently, sample means that are close in value to each other result in a small F-test statistic and a large p-value. So we can conclude that there are no significant differences among the sample means. Sample means that are very far apart in a value result in a large F-test statistic and a small p-value. So we reject the claim of equal means. Calculating the test statistic F with equal sample sizes n. If the data sets all have the same sample size, the following calculations aren't too difficult. Step 1, find the variance between samples. Calculate the variance between samples by evaluating ns sub x bar squared, where s sub x bar squared is the variance of the sample means and n is the size of each of the samples. That is, consider the sample means to be an ordinary set of values and calculate the variance. Find the variance within samples. Estimate the variance within samples by calculating s sub p squared, which is the pooled variance obtained by finding the mean of the sample variances. Step 3, calculate the test statistic. Evaluate the F-test statistic with the formula given earlier. F equals variance between samples divided by variance within samples. The critical value of F is found by assuming a right-tailed test because large values of F correspond to significant differences among means. With k samples having n values, the numbers of degrees of freedom are as follows. Degrees of freedom using k equals number of samples and n equals sample size. Numerator degrees of freedom is equal to k minus 1, and denominator degrees of freedom is equal to k times n minus 1. The F-test statistic is very sensitive to sample means, even though it is obtained through 2 different estimates of the common population variance.